In the last lecture we were looking at solving the diffusion equation for transport in the limit of low Peclet number. Okay. As I told you in the last lecture, the most general form of the conservation equation, okay, containing the time derivative, the convective transport, the diffusive transport and the source term, when scaled, reduces to a form where there is a Peclet number multiplying the convective term on the left if all variables are scaled by the diffusion scales. And in that case, the equation reduces to a Poisson equation, the Laplacian of the concentration or temperature plus a source is equal to 0, or the Laplace equation if there is no source. And the general procedure for solving this equation is the separation of variables procedure, which I had solved for you for a simple rectangular block where there is different temperatures on the 4 different walls in order to determine the temperature throughout the domain by solving the Laplace equation for the temperature in two dimensions. The procedure: write down the temperature as a function of x times a function of y, substitute, divide by x and y, and you will get one term on the left which is only a function of x, the second only a function of y, therefore both have to be constants. The constant in the homogeneous direction, in this case the x direction, is in the form of discrete eigenvalues I pi by L in order to satisfy the boundary condition that the temperature has to be 0 at both x is equal to 0 and at x is equal to L. So, the temperature was a form sine of I pi x by L. In the other direction, the inhomogeneous direction, the solution was in the form of exponentials e power plus I pi y by L and e power minus I pi y by L. Substitute that into the boundary conditions and then use the orthogonality relation, okay, in order to find out the coefficients. Okay. So, that is the general procedure. Here we will solve the next problem, which is the flow in a rectangular channel. Okay. Okay. Of height h, width w, okay, and we will assume it is a unidirectional flow. So, there is no variation of velocity with respect to the x direction. Okay. So, the directions in this case are x, okay, is in the horizontal I am sorry, y is in the horizontal direction, please correct that, and z is in the vertical direction, and x is in the streamwise direction. Okay. So, there is flow in the x direction, there is a velocity Vx which is flowing in the x direction due to a pressure gradient exerted across the ends of the channel. The flow is assumed to be steady and unidirectional, which means that Vx is only a function of the y and z directions, fully developed. Therefore, there is no variation in the velocity in the x direction. Okay, it is fully developed because so that there is no variation in the velocity in the x direction. And this is driven by a pressure gradient dP by dx. Okay. If you recall, when we solved the equations for the flow in a pipe, I had told you that for a steady fully developed flow, the pressure gradient is a constant, dP by dx is a constant, it is independent of x. And the pressure is also a constant in the y and z directions because there is no velocity in those directions, and therefore, there is no force that can cause a pressure variation in those two directions, which means that the pressure is only a function of the streamwise x direction and dP by dx is a constant. Okay. The conservation equation for a steady fully developed flow, if you recall, 0 was equal to minus dp by dx plus the viscosity into partial square Vx by partial z square. This was for a two-dimensional channel. So, this was for a this was for a flow in a parabolic flow in a channel, in which there was variation only in the z direction, variation of the x velocity in the z direction, and there was no variation in the y direction. We had assumed that it was infinite in the y direction. If you have a wall, a side wall in the y direction as well, then this equation gets slightly modified, partial square Vx by partial y square. So, this is the Laplacian of the velocity in two dimensions. If you recall, I told you that the Laplacian of the velocity appears in the momentum conservation equation. You had the inertial terms on the left. Let me write that down for you. This is the general equation. You can write that in a Cartesian coordinate system for the three components. I will leave that as an exercise for you to show that for a unidirectional flow where Vx is only a function of y and z, and Vx, Vy and Vz are 0. The flow is only in the x direction. This term is identically equal to 0, and the equation for the x direction becomes minus dp by dx plus mu d square Vx by dy square plus d square Vx by dz square, for an incompressible flow, for an incompressible flow. And in the other two direction, minus dp by dy so these are the equations that you get from the Navier-Stokes equations that we had derived in terms of vectors if Vy and Vz are both equal to 0, identically equal to 0 for a unidirectional flow. You can show that. So, this is the equation and the boundary conditions. We need two boundary conditions in the x and the y direction. They are obviously the no slip conditions. Vx is equal to 0 at y is equal to 0 and y is equal to w, and in the z direction as well. The velocity is 0, no slip condition at all four boundaries. So, how do I solve this equation? Since the velocity is equal to 0 at the boundaries in both the x direction and the boundaries in the y direction, the equation can necessarily be represented as the summation of orthogonal functions which reduce to 0 in the x and y direction. You recall that I told you that these eigen functions are orthogonal, they span the space. That is, any function can be expressed as some coefficient as the summation of a coefficient times these functions, and those coefficients can be determined from the orthogonality relation. So, any function f of x in the x direction can be written as some a I sin, I am sorry, it should be y, I pi y by w, provided this function has 0 value both at y is equal to f of 0 is equal to f of w is equal to 0. Okay. If it has 0 at both boundaries, then it can always be expressed as the summation of a coefficient times sine of I pi y by w, because these functions are complete and you multiply both sides by sine of j pi y by w, integrate, use the orthogonality to determine what these coefficients are. Okay. So, this expansion is always possible. How do we determine the coefficients in the expansion? Okay. How do we determine the coefficients in the expansion? Substitute that into the equation. Okay. So, I will get minus dp by dx plus mu summation. Okay. So, let me first take the determine the derivatives. Okay. Okay, partial square Vx by partial y square. Okay. Okay. When I take the second derivative with respect to y, I get minus I pi by w the whole square. Okay. When I take the second derivative. Okay. You can easily see this by taking the two derivatives with respect to sine function. Take the first derivative, you get I pi by w times cos, and the second derivative you get minus of I pi the whole square by w square times sine. Okay. So, that is the derivative. Okay. Similarly, partial square Vx by partial z square is equal to minus j pi by h the whole square substitute that into the conservation equation, the momentum conservation equation here. Okay. So, I will get minus dp by dx minus mu whole square into this has to be equal to 0. Okay. So, basically I have just substituted these two expressions for the derivatives into this equation. And how do I determine these coefficients? I just multiply the entire equation by sine of m pi, okay, y by w, okay, sine of n pi z by h, okay, integrate dz from 0 to h integral 0 to w dy. Okay. Note that in these expressions I and j are integers in order to satisfy the 0 velocity conditions at 0 and w in the y direction and 0 and h in the z direction. Okay. So, these two have to be integers. So, I multiplied by sine functions with some other indices m and n, okay, and then use the orthogonality relation. Okay. We had just derived that, okay. Integral dy from 0 to w of sine of m pi y by w sine of I pi y by w is equal to w delta I m by 2. Okay. You recall we just derived that by using a trigonometric identity for the product of sines as the sum of cos functions. Also we had integral 0 to w dy sine of m pi y by w is equal to 1 minus 1 power m into w by m pi. You multiply the sine function by a constant and this is what we just derived. Okay. This is what we had just derived here. Okay. 1 minus 1 power m times that constant into w by, in this case, m times pi. Okay. So, when you multiply this entire equation and integrate, what you will get is minus dp by dx into these two integrals, okay, one for w and the other one for h. Okay. So, I will get 1 minus 1 power m w, okay, by m pi into I am multiplying the pressure term here by these two functions and carrying out two integrals over y and z. Okay. The first one for sine of m pi y by w, the second one for sine of n pi z by h. Okay. Okay, so, I am carrying out two integrals. Okay. So, I just get the product of these two integrals as the first term here. Okay. The second term I am multiplying, okay, mu, okay, and sigma into this coefficient I pi the whole okay, into aij into w delta I m by 2. That is, I am multiplying this sine function I pi y by w and sine of m pi y by w and integrating, and then using this orthogonality relation. Okay. Okay. Times the multiplication of the sine function here. Okay. This one with sine of n pi z by h, and I will get h delta j n by 2. Okay. This whole thing is equal to 0. Now, this summation on the second term on the left is non-zero only when I is equal to m and j is equal to n. Okay. So, I can write this as minus dp by dx into 1 minus 1 power m w by m pi okay, times W h by 4. Okay. Just substituting here, W by 2 to h by 2 gives me W h by 4, and these W and h you can see will cancel out on both terms, because these just arise from the integrals. Okay. And finally, I get an expression for A m n. Okay. Is equal to okay. So, that is the term on the right. I am sorry, that is the first term here. Okay. So, I have to multiply by the coefficient of the second term in order to get this. Okay. So, let me just okay. So, there is a factor of 4 by mu coming out of these two terms, 4 and mu here. Okay. And then there is an inverse of this term here. Okay. There is an inverse of this term. Okay. Inverse, okay, into dP by dx. Okay. The dP by dx coming out of the pressure gradient here. Okay. And there is a negative sign here, because I have a negative sign on both the first term as well as the second term. So, when I take it to the right hand side, one of them will become positive, and I will get a negative sign in this coefficient. Okay. Okay. So, therefore, the velocity V x is equal to summation I is equal to 1 to infinity, summation j is equal to 1 to infinity. Okay. Let me take the coefficients outside. Okay. Summation I is equal to 1 to infinity, whole inverse. Okay. That multiplied by sine, my apologies, I have used I and j here. So, I should use I and j here. This is I, this is j. So, this is the solution for the velocity. For a flow in a pipe, we had got a relatively simple form, a quadratic form, a parabolic profile. For a rectangular channel, you have this rather complicated form. Okay. It is a summation, of course, over sine and cosine sine functions of certain coefficients times these functions. However, this can be evaluated up to a finite number of terms to get an approximation for the velocity profile. Okay. how do we calculate the average velocity, and from that the friction factor for the channel flow, okay, just as we had done for a pipe flow. The volumetric flow rate is integral from 0 to w dy integral 0 to h dz of Vx, okay. That is the integral of the velocity over the cross section gives me the volumetric flow rate, okay. And the average velocity is going to be equal to the volumetric flow rate divided by the area of cross section, that is Wh. So, how do we evaluate the volumetric flow rate? We have to integrate this Vx over 0 to w in the y direction and 0 to h in the z direction. Note that Vx depends upon y and z only through the dependence of these sine functions, okay. These are the only functions that depend upon y and z, okay. And the integral, for example, we had just evaluated integral 0 to w dy sine of I pi y by w. We had just evaluated that as 1 minus 1 power I by w by I pi, okay. That is what we had evaluated the integral as, okay. And similarly, integral 0 to h dz sine of j pi z by h is equal to 1 minus 1 power j into h by j pi. Okay. Substituting that into these integrals, we will get that v dot is equal to all of these coefficients, okay, pass through unchanged because they are all independent of y and z. It is only the last sine functions that we have to substitute these expressions, okay. So, we can do that. This will give me minus 4 into 1 minus 1 power I, okay, into 1 minus 1 power j, okay, by I j pi square, okay, into I pi by w whole square plus j pi by h the whole square whole inverse, okay, into the product of these two terms, okay, into the product of these two terms, okay, these two integrals, okay, into the product of these two integrals. Those will just give me a factor of WH into 1 minus 1 power I the whole square, 1 minus 1 power j the whole square divided by I square, let me write that again, pi to the 4. Okay. There are two pi's here, pi square, and there is a pi square here in the denominator. So, that gives me a pi to the 4th, and of course, I have to have the summations. Okay. I have to have the summations here. So, that is the volumetric flow rate, just integral of the velocity over the two coordinates. Okay. The average velocity is the ratio of the volumetric flow rate and W times H, the cross sectional area. Okay. So, therefore, the average velocity is equal to summation I is equal to 1 to infinity, summation j is equal to 1 to infinity of minus 4 into 1 minus 1 power I whole square So, that is the average velocity. Okay. Sorry. G pi by h the whole square, whole inverse. Okay. So, that is the average velocity, and from this I have to get the friction factor as a function of the Reynolds number. I will continue this in the next lecture. I will see you then.